Hi, welcome to video number 23, Spectral Unmixing in ENVI. In the last video, I showed you how to extract a spectral reflectance curve from three different regions of interest. We had one for spruce trees, one for deciduous trees, and one for grass. In this video, I'm going to show you how to now go to an unknown pixel and figure out what percentage of spruce, deciduous, and grass might be present in that pixel. And that's going to be a process called spectral unmixing. So in this video, I'll review what spectral unmixing is, then I'll show you how to do it in ENVI, and then I'll show you how to extract the results of your spectral mixing calculation. So a quick introduction. Spectral unmixing is a technique that's used on mixed pixels. A mixed pixel is a pixel that has a ground footprint encompassing more than one surface type. So for example, in this case, this pixel has a bunch of land and also a bunch of water in the pixel. But when you're working with it in a raster image, you'll only have a single value for the whole pixel, a single reflectance value. And that reflectance value is going to be a mixture of the land contribution and the water contribution. So spectral unmixing is a technique by which we can figure out how much of each component is actually present in the pixel. So now let's look at some of the simple math behind this. And I want to start out with my first example, just imagining a one-band image in which a given pixel is a mixture of reflectance from a deciduous tree and reflectance from a spruce tree. So these are going to be our two end members. And deciduous might have a reflectance of 10 typically, and spruce surfaces might have a reflectance of 50. Now, in our single band image, we've measured a single reflectance value of 30. And we know that that value is not deciduous and it's not spruce. It's going to be a mixture, a fractional mixture of deciduous and spruce. So our first step is to set up a mixing model. And that's going to look like this. The reflectance in the pixel is equal to the fraction of deciduous cover in the pixel times the reflectivity of the deciduous cover plus the fraction of the spruce cover times the reflectivity of the spruce cover. So basically we're going to adjust the reflectivities of the deciduous and the spruce by the fraction in which they're contributing light back to our image. Okay? Now I'll substitute the values in. So I'll sub in my pixel reflectance, then I'll sub in my end member reflectance, 10 and 50. Now keep in mind now, we're in a situation where we'd like to solve for these fractions. That's our goal. But right now we have two unknowns and only one equation. So we need an additional equation to try to constrain this problem. I'll bring in this second equation, and this is called a unit sum constraint. We're going to recognize that the fraction of deciduous plus the fraction of spruce must equal 1, okay? And by doing this, by imposing this constraint, we're assuming that it's only deciduous and spruce trees that are reflecting light back to our image. And this might prove to be a bad assumption later on. But for now, we're going to make this unit sum assumption. Then we can rearrange that unit sum assumption such that fraction of spruce equals 1 minus fraction of deciduous. And I can substitute in the fraction of spruce back into this equation. And I can now solve this whole equation for the fraction of deciduous and then solve again for fraction of spruce. So we ended up with two equations, two unknowns, and we were able to solve for both fractions. So now, let's consider a multi-band image. In that last example, we only had one band, right? In a multi-band image, we actually have end member reflectance values for each band. So we have a reflectance in band 1, reflectances in band 2, 3, and so on. So effectively, instead of setting up just one mixing equation, we're now going to set up 6 different mixing equations, one for each band. even though we have 6 different bands, keep in mind that the fraction of deciduous and the fraction of spruce are going to be constant. That has to do with what's on the ground. So those fractions should be the same for all 6 bands. Okay? So in theory, we could mix these end-member spectra by the same fractions and get some predicted mixture. So that's the ideal theoretical situation. Now in reality, things are a bit messier. It may not be the case that a single mixing fraction gives a perfect match with the predicted mixture. And that could be due to variability in what's on the surface. It could be due to differences between the bands. But in any event, applying that constant mixing fraction to all the bands may give you a bit of variability when you're actually using your observed data. So this is where the power of spectral mixing comes in. The computer is able to generate predicted mixtures for a whole range of different mixing fractions. Maybe 30%, 70%, 40%, 60%, or 50-50. So it can predict what the spectral mixture would look like for all those different mixing fractions. And then it can compare the actual observed pixel value with each of those mixtures. And the ultimate goal is to determine which of the predicted mixtures most closely matches the observed mix. And this is going to be done by a technique called least squares inversion. And what this technique does, it looks at what the predicted mixture would be for a given set of mixing fractions, and then it looks at the observed data. It calculates the difference between the predicted and the observed for each band and squares it. That's this row of data down here. Then it sums those squared differences across all the bands. One way to do this is by trial and error. Try a bunch of different predicted mixtures and see which one gives you the lowest summed square of the differences here. And that's called a least squares fit. Now in practice, there's never going to be a perfect fit, but you're going to find the one in which the differences between all the bands is the least, as measured by the sum of the squares. And that's going to be your best fit mixing parameters. Now, of course, ENVI is going to go through and do this calculation for every pixel, and it's going to spit out the least squares fit mixing fractions for every pixel. So let's go ahead now and look at how we can actually do this in ENVI. So I've got my ENVI project open already. Here's my multi-band Landsat that I've stacked for the Middlebury area. Here's the regions of interest I made. This was the spruce, this was the deciduous, and this was the grass. So these 3 are going to be our end members in our mixing calculation. And we're going to try to figure out for each pixel in this image what fraction is deciduous, what fraction spruce, and what fraction grass. So recall in the last video, we set up these regions of interest and we exported the mean spectral reflectance for each of those polygons. And so we exported those as statistics files, and we're going to use those now as our mixing end members. So to do our mixing calculation, we'll go over to the toolbox under spectral. Then we'll find spectral unmixing. And we're going to choose linear spectral unmixing. I'm going to choose the stacked Landsat as my target for data. We're going to do the whole scene. We're going to use all the bands. So I'll hit that. Now here is the interface that asks me to specify what end members I'd like to use in the mixing calculation. I'm going to go ahead to import from statistics file. Note that you've got a bunch of different options if you'd like to use different things. But in this case, I'll use the statistics files that we created. So here's my deciduous, here's my grass, and here's my spruce. By the way, if you haven't made these, you should stop now and go back and make these. So now I've got 3 possible end members. I'm going to hold down Shift, highlight all three, and then I'm going to hit Apply. Here I'm going to apply the unit sum constraint. This means that I'm going to force all of the fractions to sum to 1. You don't necessarily need to do this, but it can be a good idea. Now I'll hit Choose, and I'm going to save this in my output. I'm going to call it vegmix2. I'll use a .tiff extension. Aha, and up comes the image. So here is our spectral mixture image. So before I consider this RGB mixture, I want to first go to my data manager and show you that the spectral mixing output actually produced 4 different rasters. It produced one raster for the fraction of deciduous, one for the fraction of grass, and one for the fraction of spruce. It also produced one that shows the root mean squared error, or the uncertainty on the mixing calculation. In other words, how well was it able to match those spectra when it tried to do the least squares solution. I'm going to try to load one of these as a grayscale here. I'll right-click Load Grayscale. So this is the fraction of deciduous trees, okay? Notice that if we go back over to our source area, the highest values are in white. You can see they're pretty darn close to 1 out here, pretty darn close to 1 out here. So those are areas of almost pure deciduous trees. Likewise, this darker stuff up here is going to be closer to pure spruce trees. I'll also quickly visualize that root mean squared error raster. So bright values have really high errors, dark values have low errors. Notice that the lowest values are out here in the forest, where we were able to get a pretty good mixture between spruce and deciduous trees. So those were low errors and good fits. Down here in town, we're getting really high errors, these bright colors. That's because, for example, this location is a quarry. There's no vegetation at all, so the unmixing algorithm was not able to find a good solution using the vegetation end members. Okay, and finally we're back to this RGB image where red is the fraction of spruce, green is the fraction of grass, and blue is the fraction of deciduous trees. And this looks pretty good. Remember the summits of Breadloaf Mountain here, showing up red with the high fraction of spruce. The flanks of Breadloaf Mountain showing up blue with high fractions of deciduous trees. The agricultural fields in town showing up a strong green, because those came out with high fractions of grass. So this spectral unmixing looked like it worked out really, really well. So the final thing I want to show you now is how to extract the mixing statistics for any specific area. And we're going to do this by just making another vector and turning it into a region of interest. So why don't we zoom in actually on the flanks of Breadloaf Mountain. I know for a fact that these are mixed spruce deciduous forests. I'm going to create a new vector layer. I'll call it mix results. It's going to be a polygon. I'm going to coordinate it with the mixed result. Okay, now I'm going to edit it. I've showed you how to do this already. I'm going to make a single polygon. I'd like to know what the average fraction of spruce and average fraction of deciduous is for this polygon. So I'm going to first save it as a shapefile. Okay, I'm going to go over here, convert vector to region of interest. I'm going to choose the mix results. I'll choose unique records. Now importantly, I want to extract the results not from the original Landsat stack, but from our new mixing results. So that's vegmix2. So it produced the ROI. Notice it's held under the vegmix2. I'll right click and I'll look at the stats, where band 1 here is fraction of spruce, band 2 fraction of grass, and band 3 fraction of deciduous. So band 3 is fraction of deciduous, band 2 is fraction of grass, band 1 is fraction of spruce. Okay? So the mean values are 52% spruce, 43% deciduous. Of course, I can save these as a stats file and work with these mean values in any way that I would like to. Well, thanks very much for listening. To recap, you learned a bit about what spectral unmixing is. You learned how to do spectral unmixing in ENVI, and then you learned how to use an ROI to extract the results of your spectral mixing calculation. Please definitely join us for our next video. Will sings his favorite Lady Gaga songs.